theoretical part of the eruptions, and we're going to start with Sergei talking about planets and non-ideal MHD disk in FUOR eruptions.
Thank you very much. As you can see, I've changed my talk title a little bit, getting rid of disciplines, just because there's not going to be enough time for me to go through that. So I have my collaborators here in that list. Verdun is the most influential in this work, and of course he'll talk on a different but related topic a bit later today. So with this, let me start with binaries. There's a good reason for us to learn from the field, and that is because this is the best laboratory of accretion disks. These systems are not heavily obscured because we can measure the periods in this system, the binary period. We know the sizes of the disks, the masses of a component, and that gives a great laboratory. The time scales are shorter for the outbursts, so you can easily live through lots of outbursts. We can't really do that with FUOR type outbursts. So, yeah, we need to learn. Right, so in 1973, Shakura and Sinyaev developed this theory, which now is called standard accretion disk theory. On the bottom there is the main equation of that theory, which relates the disk viscosity to the time evolution of the 1D azimuthally averaged disk surface density sigma. And a steady state, this theory gives you constant accretion rate through your disk. But everything depends, you see, on this kinematic viscosity coefficient, which depends on disk physics, depends on the ionization state and the opacity of the disk. And so you actually need to solve for the thermal equilibrium of the disk for D. And when you do that, you get these results. This is from the seminal paper by Bell and Lin in 1994, where we show you effective temperature versus sigma in the disk for one specific radius. And there are 4 curves computed for the alpha coefficients from 10 to minus 4 to 10 to minus 1. And critically, what you have is 2 stable branches, cold stable branch and a hot stable branch. Okay, see, I can use a pointer, right? How do I do that? Sorry? Okay. Right, let's see. Yeah, can't really do it. Okay, well, so the middle branch there is thermally unstable. You see, and so when you put it in that time-dependent code, you get this characteristic behavior. You have a system spending most of the time in the cold, stable state, but then it goes in outburst on the hot branch where hydrogen is ionized, and that gives you an outburst, right? So of course we do observe outbursts in stellar binaries, in cataclysmic variables, CVs. The other name for this is dwarf nova. So these are disks around white dwarfs, and then we observe outbursts in systems where the primary is a neutron star or a black hole. They're called low mass X-ray binaries. These systems is that what the people in this field were able to do is were able to deduce the time average accretion rate in these systems, because we have, lots of these outbursts, right? And then in these papers, this plot is in particular from Lubus et al. In 2018. What we show is the distribution rate for different systems as a function of the binary period. Okay, binary period is important because that sets the size of your accretion disk. And the theory predicts the accretion rate for which the whole of your disk is on the edge of S curve, okay, on up there on the hot branch. And that scale is a binary period, like this, red line. And so what we show here in red are systems that are always stable from observations. The rest are unstable. Okay, so that's exactly with the observations, and you can also plot this for low mass X-ray. But there are, around 200 systems in total, and practically all of them are consistent with this prediction. Okay, and so what this tells us is that while there are still many puzzles in that field, in terms of the shape of the outbursts, behavior and wavelengths and so on, but terminal stability is definitely critical for understanding these systems. So, unsurprisingly, Bell and Lin suggested that this scenario might also apply for FUOR type systems, right? But to produce reasonable models for these systems, we had to require that alpha is about 100 times smaller than what predicted by numerical simulations of the MRI, which we think gives us the alpha in ionized accretion disks. Okay, and the reason for that is quite simple. So on the top I have this equation which gives you disk time. You evaluate it in state of a disk on this hot stable branch. Then it's about 1 year if the outburst propagates to about 1 AU. All right, and this scales with alpha very strongly, inversely proportional, and you can see that to make it 100 years, you need to make it 100 times smaller or so. Okay, and many people picked up on this and correctly criticized this model. Okay, and just to say that in CVs, because the size of the unstable region is much smaller, the prediction actually works very well. So there it's consistent, but not for FUOR type systems. Okay, so what happened in this field, though, is that, of course, due to white sky surveys, we've now discovered many systems with unusual characteristics, right? So here is one Gaia 20 EI, which was already mentioned, which shows repeating outbursts, which are just a couple years long. But they are strong in terms of the optical amplitude rise as your typical FUOR outburst. So, what we've tried to do is we've tried to find parameters, alpha parameters, bring alpha hot in these models. To try and feed these systems, well, this particular source and also PTF14J that Lin and collaborators discovered. And while the bits are not perfect, they are reasonable. And with alpha values that are consistent with ideal MHD simulations. So, you know, they are 0.05 or so in models. So that is promising that, you know, presumably these ideal MHD thermal stability models can explain these unusual sources. How else can we test thermal instability scenario? Well, we can't really do what people did in the CVs and low mass X-ray binaries field because we don't live for that long, right? But there's a different prediction of a theory as well. This is the minimum accretion rate when the instability sets in. So there's this there, which you see actually is very independent of alpha. This result stands, you know, it's 30 years now since, you know, that paper, but that result still stands, and that value is about times 10 to minus 7 solar masses per year. It does depend on the radius of the star. So, but you know, for I think this is 3 times 10 solar rate. That's what you get. And the point is that you see that when you look at the typical outburst, then a range of m dot is quite unlikely because the system goes through these values very rapidly, right? So what we've tried to do is so there's a sort of a forbidden range in m dot. Yeah. So what we've tried to do is we've tried to collate literature on systems where the offer is derived m dot. Okay. So we haven't derived these ourselves, but we just collated the literature. Whether the source is an EX loopy type, FUOR type, or a mixed characteristic type, we put it in this sample. We have, I think, slightly over 3 dozen sources in here. And you can see a gap. Okay, well, there are error bars, of course, so you can either take lower limit that people derive to upper limit. That's what we've done, right? And there are probably more uncertainties, but you can still see a gap. Okay, that desert, which is in the right place for thermal instability scenario, and I think it's actually pretty strong, this gap, because if my errors are random in distribution, then any sharp feature in a real distribution would be smoothed out. So the fact that you still see it, to me, it exists in real systems. Okay, so I would say that it's possible that one thing I forgot to mention is that if you then look at how these systems are were classified in the publications, then the sources for lower accretion rates there, while these ones are a FUOR type. Okay, so it's possible that thermal instability is for that separates systems that go into these outbursts and those that stay in a smaller outbursts. Okay, but of course, thermal instability does not by itself explain why FUOR outbursts are so long. So we've said in that paper that we need something else. Okay, and that something else should be something that doesn't happen in binary systems, right? Because in binary systems, thermal works pretty well, as we said. Well, what do we have that we don't have in binaries? First of all, planets. Yeah, we don't have planets in binary systems. And then non-ideal MHD. Why non-ideal MHD? Well, this is because these systems are much smaller, and we also have a secondary star right there. So they're hotter, okay? And most of them are in the ideal MHD limit, right? I mean, people do query there some of the systems as well, but for protoplanetary disks, it is absolutely obvious that there are regions where non-ideal MHD applies, right? And then, of course, there could be something else, and we will hear about our ideas on other scenarios for FUOR outbursts later on today. So just focusing on the planets, there are two ways in which planets can interact with disks. The first is simpler, because in this scenario, nothing happens to a point mass, and the way it affects the disk is just through gravitational torques. So Laudata and Clark explored this scenario in 2004 in particular, and I'll discuss our recent work on it in a moment. Then also the planet could be destroyed during outbursts, right? And Edward and co-authors have done a lot of work on that, and I'll mention that on the slides as well. Okay, so what happens when we have just gravity? So this slide here is a preliminary simulations from 2D runs done by a PhD, final year PhD student, Yin-Hao Wu, working with me and Lester. And they're preliminary, so I'm not ready yet to share results. We still need to, do more work. But it illustrates well the fact that a gap in the disk, of course, as in ALMA scale disks, right, on tens of U. The same thing can happen on much smaller scales if a planet is massive enough. But of course, physics here is richer, because for ALMA, the disks are essentially isothermal, heated by the star, okay? So here, the system is much more non-linear, because the disk is being self-heated by accretion, but also planet also can heat up the disk through gravitational torque. So what might happen is that during quiescence, you have two disks that are basically separated from one another, and mass doesn't communicate easily from one disk to the other. But outburst, the disk becomes hotter, and you can have mass overflowing the gap, and these two volumes then become communicating. Okay, so and also what is possible, as shown by Laudata and Clark, is it's the outer disk that the outburst can happen, can start, rather than the inner disk. So then you have an outburst from outside in, and that is really important for outburst properties. So we tried to apply this to Gaia 20 EIE, and this is busy plot with lots of panels. But if you just focus on this panel, which shows central temperature at different times, the times are there. So this is just a year or so in an outburst. But you see, the outburst actually happens here. So it starts twice, and then the ionization front propagates then through the gap and then goes to the star. Interesting in this is that this gives you sort of a step in the outburst. So this plot here on the bottom shows the accretion rate onto the star in black, the accretion rate, the mass flow rather, through the gap, okay, through position of a planet in red. And so you see that starts earlier, okay, and when enough material has flown through the gap of the outburst beginning in, well, the instability beginning in the inner disk, and then you get this precursor. So the fit again is not perfect to this outburst. It's better than the planet. So we try and test it. Okay, so now let's talk about what happens if you if your planets can be destroyed. So GI, gravitationally unstable disk simulations show formation of these clumps, which then migrate rapidly in. Many people with different codes, including myself, saw this process happening. So that gives you a burst. But of course, when these simulations, the 2D or 3D simulations for thousands of years, for well, Edward runs them for up to 1 million. You can't really resolve the inner 10 AU or so. But of course, the outbursts happen much closer in, right? So we need to somehow resolve that region. And so far, we've only been able to do it in 1D. We've done this with Giuseppe Lodato. What we've done is we've looked into that equation, adding the gravitational torques term and also the mass loss term from the planet. The planet loses mass in here by Earth lobe overflow. So this is tidal disruption. The planet needs to be really large, 30 Jupiter radii. So there's still clump cooling down from an initial collapse in the disk. You do get an outburst, but it's a very short, very powerful outburst, not like those we see in right? So that's basically what the state of sort of my thinking on that for years, until I happened to talk to James Owen a couple of years ago. Because James studied photo evaporation of planets lower mass planet. But then we started thinking about, well, in temperature, outbursts, something like 30,000 K. So the disk is so hot that you can actually, heat up the outer layer of the planet by radiation diffusing into the planet. The disk is hotter than the planet. It can then start touching that planet. So we worked out an analytical 1D theory for planet evaporation, okay, and checked it against 1D numerical integration. And the great thing about this is that this is a self-limiting process. It's a steady state process. So we've added it to the code just to say that basically this last term on the right becomes now a function of disk temperature, but of course disk temperature depends on sigma, on alpha. So this is 1D system. The planet is in 1D and the disk is treated in 1D, but it is quite a nonlinear system of equations, and it doesn't have to work, okay? But this is what you get. So this is a movie. What you have. The planet is the top panel shows you sigma. The lower panel shows you midplane disk temperature. And first these typical thermal instability bursts. right? Nothing happens to the planet until it gets to the. I'll stop here for a second. Oh, sorry. It gets to the region where the disk is hot enough to start evaporating. You have a steady state for hundreds of years until the planet is completely destroyed and then the thermal instability restarts. It gives you lots of things actually match FUOR outbursts. So I think this is interesting. And this scenario does resolve, in my mind, this, one of the biggest puzzles and why the outbursts are so long. Okay, but of course we need lots of these evaporating planets, right? Many people in the field would say, well, that's crazy because we don't have that many gas giant planets. Well, we don't have them again, around mature stars, but the simulations show that you can form that many clusters in the disks, and perhaps you destroyed 99% of them, right? So there's not necessarily a contradiction there, but we do need to go because these are still very, very simple models. Okay, so I in detail, I don't quite trust myself yet on these results. I think it's promising. We need to do more there. Okay, however, so earlier this year, very interesting publications came out from VVX survey. So this slide is this plot is from et al. It shows you the KS amplitude rises in these bursts versus the rise time. And importantly, you can see that, and this is only FUOR type objects on this plot, by the way. You can see that these rises can be quite large, comparable to the optical rises. Okay, and this is not what ideal MHD models predict. I will be back to this slide in a moment to explain it. Sorry, how am I doing on time? Okay, that's, yeah. That? Okay, so the reason why the ideal MHD actually can't predict you such a strong outbursts is that the S-curve from ideal MHD has a relatively small stability region. Okay, so this, the dots there are from 3D simulation by Heroes in 2015. And this instability region is too small, okay? So that doesn't actually give you strong enough bursts in KS. They're strong in the optical, but not strong enough in KS. But if you assume that alpha is smaller on the cold stable branch than the ideal simulations give you, due to non-ideal MHD effect. So this is a very simple scenario here. I'm just saying that our cold is smaller than 0.03, right? And these are for different alpha cold there. But it's constant on this branch, which is not quite physically self-consistent, but you see that the instability region in the S-curve increases, so that gives you stronger outbursts. Okay, so that can, in principle, work. And before I finish up, I also want to say how this relates to previous work. Well, in the past, so Phil Armitage proposed this very important model of dead zone or MRI activation scenario for the instabilities and a few ORI type systems, just based on Charles Gamy layered accretion disk model. You form the dead zone with zero viscosity in the intermediate range of radii, and then enough mass accumulates there. The disk is ionized, usually by the gravitational stability in that region, which heats up the disks. And you get these nice outbursts. And lots of people did simulations in 1D, 2D, and the models was thought to be quite promising. However, more recent 3D non-ideal MHD simulations show that these dead zones don't actually form because you have MHD disk-driven winds, which continue to transport material through the dead zone. And also there are other effects that do not give you alpha equal to even if you doesn't think that model applies this, okay? The other reason why it can't really work in setting is that what we need to do is to combine the physics that we know from binaries with this scenario, because in the inner disk, which was in the inner point 1, which really properly numerically resolved in Field's original paper. If you do include the physics of both of these scenarios, then actually each of these individual nice low bursts that you get from dead zone activation into lots of much shorter thermal instability bursts, because essentially your dead zone activation just provides you with an accretion rate flow through this region that can't go at a fixed rate through the region, so you get lots of that burst. Near-infrared interferometry by LICO and calibrators also challenges this result quite strongly. So what we do need is a model that combines two. I don't think that, that model doesn't yet exist. It is a very difficult problem, but I think how we can make progress if we observe these disks in quiescence just before an outburst or post-outburst, that can help a lot. So here are two recent papers, two recent system. This is from Jean et al. And this is from Trond and Hillebrand. What's common to these two systems is that in quiescence, so the way these systems have some data pre-burst to try and plot SADs. And what's interesting is that you try and fit this component here with a black body, and the temperature you get is about 600 K there, and I think 700 K also here. Okay, and that is very interesting. And sorry, just to say that it definitely contradicts these models, because here you get temperature of 2000 K before the instability occurs. Okay, so that definitely rules out ideal MHD and requires non-ideal MHD in these models. But how you do it, that's a difficult question. Okay, so just to conclude, I think thermal stability is definitely a feature in FUOR type outbursts. There are some sister planners can help, I think. We need more work on that. And data definitely tell us that we need non-ideal MHD. Okay, that's it.
Yeah, thank you, Sergei. So we have a bit of time. I want to start with a student question. So if there is anybody, Daniel?
Hi. Yeah. Sorry. Hi. Really interesting. So I want to know about the output. in the planet case, so specifically in the case where the outburst doesn't affect the planet, that doesn't like only affect the gravitational torques. So I don't know if I missed something, but what happened with the migration of the planet in this case? So it's infall, it's changed a bit,
Yeah,
or
thank you for the question. Well, so if you look at you will see what happens. Let me just see if this slide is from that paper. So actually, it shows the disk surface density at different times, so in years, and initially the planet opens such a deep gap that so this is, say, position of a planet here at that time. It's sigma at that time, see, and there's nothing in the inner disk. So the inner disk actually is completely empty. So there are no outbursts there at all. So the planet actually turns off outbursts for a little, which is interesting in itself. But as the planet migrates in, and in this model it migrated on timescales a few times, 10 to 3 years. Eventually, you see sigma here builds up enough to trigger an outburst, but it happens there, and then it's able, the gas is able to fill the inner disk, and that's what's the outburst. So I mean, there's lots of different scenarios, so that depends on the planet mass, on disk viscosity, what exactly happens. It's unexplored territory, really. But at this point, I don't really want to explore too much in 1D. I think you need to go to do better.
Thank you.
Okay. Could you go back to your dead zone slide?
Yeah. Is it this one?
Yeah. Thank you. So I'm trying to make two quick comments. So all this split into dozens of bursts, right? It turns out that that was kind of an artifact of having our inner radius too large. So it was right near where the TI was being activated. If you push the inner in, then you don't get it in those models, because you're not right at the sensitive place where it goes up and down. So you can actually have a pretty smooth flow, even going from the non-ideal to the TI to those at all. And it was an artifact of just having the inner boundary condition right where the TI was being activated. Second thing is, in terms of how far out you have the active region, I think that one has to go back and look more carefully at the Liku prediction and see whether it can go further, because there's always sensitivity limits in these situations. So in terms of GI, the models were being fed from outside, so you had this triggering at 2, 3, right? But you might have a distinction between whether it's GI triggered or something else triggered, but it's still the non-ideal part. And that gives you long time scales and enough stuff, right?
Yeah, I agree with both of your points, and I actually, killed my summer trying to build better models that would trigger the outbursts, and this firmly triggered outbursts rather than by GI. And there is some promise in there. We can talk more for one specific system, but the outburst I found, still too short. It's still, very hard. But it's where you actually need to go.
2 more questions. The first one from Ashish.
Yeah. Hi. I was just curious that can we test some of these ideas by comparing ALMA observations of outbursting sources and non-outbursting sources?
Well, I think that's difficult because with ALMA, right, you probe scales that are much larger than this. I mean, that's the issue with ALMA for this system. That's why you need, you know, optical and near-infrared interferometry. I'm hoping that we can do it if, yeah. You know, optical, yeah, near-infrared interferometry, but even that is very hard, right? Because you need very bright systems and our, you know, bright. So yeah, I think that's trouble. No, I think it's too hard with ALMA.
Thanks.
Talk. I am curious to know a little bit more about the those transover region, the turnover regions in those ACE curves of the TI instability curves. I just want to know that what exactly triggers, I mean, what is the physical mechanism that triggers those ACE turns? I mean, you mentioned in one of your earlier slides that it corresponds to some m dot 5 times 10 to the minus 7, but what is the physical significance? What's really going on there in terms, or like how I can know that how sharp or how shallow the turns will be?
Yeah.
What controls those?
Yeah, that's a very important question. I mean, you should really read up, you know, on some of the review papers that I mentioned, and also Bell and Lin in 1994. Sure. But basically, what happens is this is the effective temperature in the disk. But in these calculations, what you do is you calculate the thermal vertical structure in disk. So you start from say the disk midplane is much hotter, okay, than this. And you integrate your equations, assuming radiative energy and convection, upwards until you find what it corresponds to in terms of effective temperature. And then you see the opacity is a very nonlinear function of the temperature in your disk. And there are very strong opacity transitions when, well, there's a water molecule that influences, but the most important one is the hydrogen negative ion in there, and it's the opacity changes so much that leads to thermal instability. This is a classical topic and, you know, in accretion disk theory. But there is quite a lot to read up on there, so you have to.
Yeah. Perhaps I should catch you over the tea break.
It's the opacity transition. So I must say that these are quite uncertain if you really look into that, because it depends on how also the heat is distributed in the disk. These always assume constant alpha in your disk, but because that's not quite realistic, and, you know, yeah, lots of that's what we typically do in this field, and we need to do better.
Yeah. Okay. Yeah. Thanks for your comments.
Okay, let's thank Sergei again. And the next contribution is going to be online. It's by Eduardo Vorobiev, who's going to tell us about the mystery of FE Orionis resolved.
Okay, thank you. I'm trying to turn on the share